Hello, my name is Abed Soleimani, Research Assistant at University of Alberta, Canada. I want to present my work, a domain-adapted machine learning approach for visual evaluation and interpretation of robot-assisted surgery skills. Robot-assisted surgery is becoming more popular in modern clinical practice. It has some disadvantages, such as unsafe behavior of the robot or requirement of special skills. However, it has several advantages, including fewer complications, such as surgical site infections, less pain and blood loss, quicker recovery, smaller and less noticeable scars, and above all, access to surgical procedure data. An important point here is that a surgeon must acquire a sufficient amount of skills before operating on real patients. There are two main types of evaluation methods: conventional methods, which are based on checklists and are expensive, time-consuming, prone to human bias, and they will return global scores for a given task. And data-driven methods, which are fast and accurate, and they will provide interoperative feedbacks. Due to the availability of surgical procedure data, we can use artificial intelligence for automating the surgical skills assessment. In this research, we will focus on the second type of evaluation. AI-powered surgical skills evaluation methods fall into three main groups. In inductive methods, feature extraction, model structure, and hyperparameters mostly determined by the input data, which is usually big data. This will reduce the training effort with the cost of losing models' transparency. Domain knowledge or feature-based models, on the other hand, rely on the features that are already known by human intuition or from dynamical equations of the system. This will increase the transparency and explainability of the model with the cost of introducing human bias. Domain-adapted models utilize both handcrafted features and extracted attributes from the end-to-end learning methods. These methods benefit from the advantages of both mentioned approaches and relax the disadvantages of the mentioned approaches. All the work done in the first and second categories suffer from being less transparent, or they extract some primary and sufficient features. To remedy these problems, we incorporated a domain-adapted approach which utilizes high-level features and also takes care of the explainability of the resultant model. The core idea of this research is based on the results extracted from crowdsourced assessment of technical skills papers. These papers simply say that a casual observer can discover and rate the skills level of a surgeon with comparable accuracy to an experienced surgical mentor. There are several clinically accepted metrics that are easy to detect and rate even by a casual observer: smoothness, fluidity of motion, and economy of motion. Fluidity of motion reflects how quick and accurate a task is done in translational or rotational space and can be derived from the time derivatives of the input trajectory. Economy of motion reflects the total energy demand for accomplishing a particular task and is a generally accepted factor contributing in skills assessment of various activities. As we stated in the paper, it has deep connections with the kinetic energy of the task. The most challenging feature in terms of extraction is the smoothness. Consider we have two huge fabricated datasets containing randomly generated smooth and ternary trajectories, XS and XN. These two sets share considerable similarities in terms of main variations, but we are interested in a special attributes in trajectories, which is tremor. Since the tremor is quite negligible compared to main variations of the trajectory, they can be neglected in feature extraction procedure. A good approach for capturing this is contrastive learning paradigm, in which we try to extract features that are rich in target dataset and remove shared features between target and background datasets. First, we calculate the covariance matrix for both datasets, and then calculate the contrastive covariance matrix C_C with the contrastive strength parameter alpha, and then apply normal PCA on that. As it is clear from the figures, this method returns contrastive principal components that fully separate smooth and ternary data. Each of the above-mentioned metrics is not comprehensive enough to reflect the skill level of the user during the execution of the trajectory, but together they can do great jobs. We can concatenate all of the extracted features and fit them to downstream tasks, which can be classifier network or a data visualization technique. To give a better understanding about the features to the mentors, it is a good idea to visualize data by dimensionality reduction and data visualization techniques. One of the most powerful tools in this area is t-SNE, which has a good reputation in the scientific world. To do so, we designed an experiment in which each participant tracked a predetermined squiggly line using Phantom Premium 1.8 haptic device with his or her dominant and non-dominant hands. As you can see, there is a significant difference between the performance of the trials done by the dominant hand or expert data and with ones performed by the non-dominant hand or novice data. We applied the same procedure to 3 different tasks of the JIGSAWS dataset. As it is clear, trials of 2 expert users and 1 intermediate user cluster, the second intermediate cluster in this figure, cluster close to each other and create the good cluster G, and each participant has its own subcluster. In fact, participants with higher level of expertise perform each trial in a more consistent manner relative to less experienced ones. Such hidden information cannot be revealed by classification techniques or cannot be fully trusted in the data-driven models. Another important point about the cluster G is existence of the second intermediate user near to expert users. Manual annotations with several labels are usually coarse-grained, and our approach reveals their limitations. The global rating scores assigned to the second intermediate user indicates that he or she performed very close to expert users. In conclusion, in this paper, a novel domain-adapted approach for the evaluation, interpretation, and visualization of surgical maneuvers was presented. Inspired by domain knowledge, we defined clinically meaningful features for evaluating the skills level of surgical tasks. The visualization of the ensemble of extracted features in the three-dimensional space using t-SNE technique for both experimental data gathered from the Phantom robot and JIGSAWS dataset showed that our approach can meaningfully express skills level, abnormality, and hidden information within a given surgical trajectory. The explainability and transparency of our approach makes it more reliable, safe, and interpretable compared to other state-of-the-art black box models in the field of skills assessment of surgical tasks. Thank you so much for your attention.